All right, so I wanted to talk to you guys real quick about just kind of clarifying some things on Lab 3. In terms of what you're asked to do, right, we are asking you to build on your PCB everything. So this is the complete system, okay? So I show here that I've got a PV panel, this capacitor here on the DC side, and I have this inverter, okay? I then have a filter at the output that could go to the grid, all right? There is signal conditioning circuits that take IPV and VPV. Those are the only ones you are required to do, all right? Those are the only ones you're required to do. I said you can do iGrid if you want to, okay? So IPV and VPV you're required to do. These signal conditioning circuits can effectively be almost the exact same thing that you had in Lab 1, all right? They should use the LM324, okay? You should design them using the LM324, okay? I'll talk about that here in a little bit, all right? Outputs in the signal conditioning circuits will go into the microcontroller. The microcontroller will output stuff to the PWM. The things in the blue boxes, so the signal conditioning circuits, the DC-AC inverter, and this capacitor are the things that are on your PCB, okay? All right. Now, just to kind of understand a little bit and to break this down, all right, effectively we said your board should probably end up looking something like this. Now what I've indicated on here is a couple of different types of connectors, all right? I'm going to talk about these here real quick. All right, before I do that though, what I want to do is point out a couple of things. All right, so up on Canvas, let me go to Canvas. All right, there are two modules that we've created for Lab 3. All right, this one here called Lab 3 Materials, and then this one here for Components for Lab 3. All right. What I want to do is kind of walk you through why we've put these here. All right, if I look at the schematic, and I've got the schematic up here, I have put in a schematic for the half bridge. Now this is an updated schematic from what you guys had in Lab 2, because there was a tiny mistake with respect to this portion of it. This is completely correct. All right, we know this guy to be correct. All right. This is a half bridge. You need to make, for this DC-AC inverter, you need to make a full bridge. A full bridge is, as we've talked about before, a full bridge is essentially two half bridges, right? This is a half bridge. This is a half bridge, okay? You guys are making two of those half bridges connected to the same DC bus. All right, so a full bridge, if you look at S1 and S2 in this image, S1 and S2 are a half bridge. S3 and S4 are a half bridge, right? Those two half bridges are connected across the same bus. That is a full bridge. That's what you guys are actually building. Now, the schematic for a half bridge is this, all right? What I have is 12 volts coming in, create an isolated 12 volts, have this 7805 that powers up the gate drive input and the output side of the isolator, okay? All right, then I've got my MOSFETs, okay? So this is the basic circuit for a half bridge. This is the half bridge, not a full bridge, half bridge, okay? I've said that a lot, but just make sure that's clear. Now, for this, there are two documents, or two sets of things that are useful on Canvas. One of these, all right, so I've got this module here that lists essentially the components you need. So the gate driver components, the isolator, the MOSFETs. The MOSFETs are the, no, I didn't include the MOSFETs, I'll add those. The MOSFETs are IRF 540s, all right? I'll add those in. The isolated power supply is this PDM2 S12. The 7805 is the regulator. The MER 120 is the diode. All right. One of the things that we have done is we have also created, originally earlier in the week, we had put up this BOM, bill of materials, with a bunch of different connectors that we said to use. I have updated that to include this little table right here, okay? This table indicates, essentially, it matches up with the schematic. So if I see C1, should be a 1 microfarad, 50 volt electrolytic. C2 should be a 1 microfarad, 50 volt electrolytic. So I keep going through that list. Now, for all of the capacitors here, you'll see above that Shandon had created a list here. So the 1 microfarad electrolytic 50 volts. If you click on this link, you'll get the data sheet for this guy, which will allow you to create your footprint. Okay? Use the stuff that's here that either you can get to from these links or that you can get to in this module. All right? If you don't use those, you're using components different than the ones that we're kind of specifying, and that can be problematic. Okay? Everything you need should be here. All right? Now, for the resistors, and this is true for all the resistors that you do, you will use 1/4 watt carbon film resistors. Those are the resistors that you guys use on a regular basis, 1/4 watt carbon films. Okay? Just so you understand, I have uploaded this guy, which has for me all of the information I need on 1/4 watt carbon film resistors. All right, so I can see from this guy, a 1/4 watt carbon film. So looks like there's two types. This CFR25S and CFR-25 are both 1/4 watt. So I look up here, you have the normal style, right? You guys don't use miniature ones, you use the normal style. So the CFR25 has these dimensions, which you then need to match up with this image, okay? That's not too hard to do. You guys will be able to figure out how to do that pretty easily, okay? All right, so that one's probably the trickiest one. All right, but if you go through this BOM, right, for each of the capacitors, you can go through these links here, you can get to the data sheets, and then for everything else here, the data sheets should be there on Canvas, so you can kind of go through and figure out how to populate everything in, okay? All right, now again, I said this is a half bridge. Okay, it's not a full bridge. The full bridge would essentially be a duplicate version of this in addition to this. Okay, now I say it's essentially that. It's not quite that. All right, so I want to go back real quick to a lecture that we had a while ago before spring break, back in February. All right, where I talked about this idea of isolation. All right, so when I have the full bridge, what I said, I ultimately have a situation that looks like what's shown here. All right, so I have these two half bridges, okay, and I have an isolated power supply that provides power to the half bridges, okay. Now, the reason we said we did this is because the grid is grounded. When the grid is grounded, right, I keep my microcontroller grounded. That microcontroller is powered from a regular power supply. This isolated power supply is grounded on its input side, but its output side is floating, which means that I can connect its ground wherever I want. So we connected the ground to the negative of the DC panel, right, of the PV panel. So the negative side of this H-bridge is connected to the negative of the isolated power supply's output, right? We said we did that because we had to. If this point right here was grounded, we said that this point right here could not be grounded, so we needed an isolated power supply. So the actual schematic that we used was this, okay? This 12 volt input here so the isolated power supply isn't powered directly from the grid like it's shown here, but it is powered from a grounded source, okay? So the isolated power supply is powered from a grounded source. Its output is listed as ground ISO and 12 ISO, or the net names, right? So this would be 12 ISO, this would be ground ISO, right? So everything that actually connects up, you know, basically in the driver stage, everything that is powered up in this driver stage is referenced to the DC negative. All right, if you look at this schematic, so when I say the DC negative, all right, this guy right here, so where I'm looking at in this PDF, where I've got the little hand moving over the PDF, this is the DC negative, and you will see that DC negative is connected to ground ISO, which is connected to the ground of all the ICs here. Okay, all right. Hopefully that's clear. So if I did another leg, so if I wanted to power up S3 and S4, I would power them up the exact same way. Now there is one difference. All right, there's one difference. So the fast leg, and look at the lecture on how to do sinusoidal PWM. We have one leg that's fast, right? We have one leg that's slow. So S1 and S2 will be the fast leg. The fast leg has exactly the same schematic as this. The slow leg is a little bit different. The problem with the slow leg, if you watch that video, the fast leg is moving quickly, tens of kilohertz. The slow leg is moving at 60 hertz. There's a problem with that. Okay, so the fast leg has the same schematic as what we've posted. The slow leg has almost exactly the same schematic. There is a difference though, all right? And the difference is this. All right, let me go to, all right, the whole idea behind what this driver does, right? The problem in the driver is that essentially what we have to do is to turn on the top MOSFET. When the top MOSFET is on, so in this particular example, it says up to 600 volts. When this top MOSFET is on, that means the source of that MOSFET is 600 volts. Because VGS has to be 12 volts to get the MOSFET to work, that means that with respect to this negative right here, the voltage at this gate has to be 612 volts, right? That we said was very, very difficult to do. So what we said was that inside of this driver chip, right, between VB and VS, basically, is the driver. So if I looked at this guy internally, what I would see is it's got a little driver, and that driver is powered. His positive power comes from VB, and his negative rail is at VS. Okay, so essentially what we said is that C boot, right? We said the way C boot worked was that it charged up when the bottom switch was on, and then when the top switch was on, this C boot acted as the power supply for the top driver. All right. Now so in other words, this guy is like a little battery. So it's like we charge up the battery when the bottom switch is on, and then we discharge it when the top switch is on. The problem is that we're discharging it when the top switch is on. All right, this is a small capacitor. All right, and so this concept works fine when we're operating at 30 kilohertz or 50 kilohertz or something like that. But if I'm going to try to keep this switch on for a very long time, like half of a 60 hertz cycle, this may not work. All right, this C boot may discharge, and that's going to change the operation of the circuit. So if that's the case, then what I want to do is I want to remove all of this stuff associated with C boot. In other words, I want to remove the diode. All right, so I want no connection between pin 6 and pin 3, and I don't want this C boot in there. Instead, between pins 6, so VB and VS, I need to somehow connect a power supply there. And this should be an isolated power supply. Okay. Now, you already have an isolated power supply. This isolated power supply is perfectly fine for the half bridge that operates fast. It is also fine for powering up everything in the slow leg circuit, with one exception, right? I don't want, so let me go to, let's see. I don't want, let's see. I don't want this stuff, all right? I want to get rid of that stuff, okay? What I'm going to do is between pin 6 and pin 5, I'm going to connect a second isolated power supply. All right. So what I need is a second isolated power supply. So let me go again to all right, the simplest thing. Let me do this real quick. Bear with me. Actually, let me delete this. All right, I'm gonna pull this out of here and pull it into PowerPoint. All right, and then, all right. Here's that H-bridge schematic. For the fast leg, this is fine. For the slow leg, what I want to do is I want to have another PDM. Okay. The output of that guy, so we're going to remove those components, and remove C boot. This guy would go to, so the simplest thing, so here's the plus, here's the minus, there's 12 volts. So this would go to pin 5, this would go to pin 6. All right, so the plus goes to pin 6, the negative goes to pin 5. All right. I want you guys to understand why we need to make that. Otherwise, I can make the same connection. This power supply in the slow leg can be the exact same as the power supply in the fast leg, right? In other words, 12 volt ISO can power up both gate drivers, all right? But in the slow leg gate driver, I need to replace the C5 and D boot with essentially the second version of this PDM S12 isolated power supply. You should be able to understand why that is. If you don't, you should think about it, right? All right, that's the basic approach that you're going to need to follow. All right, so hopefully that helps to explain things a little bit more, okay? Now, a couple of things that I also want to talk about here. All right. So we have a couple of connectors, right? So when I have these things, I'm going to have to bring power from a benchtop power supply in to power up all of this stuff. I'm going to have to bring power in to VDD and VSS, and then I'm going to have to bring, a connection out. So all of these guys are signals that are going back and forth from the board, and all of these inputs over here to the isolator are also signals that are going into and out of the board, okay? In this case, they're coming from the microcontroller. So now, move that to the side, and let me pull up this guy. All right, so I talked about the board design here a little bit. All right, so we talked about there being a couple of different types of connectors. Okay, so when I say PV power, that's basically VDD and VSS. All right, for that, obviously, I need a 2-position connector. And so if you look at the BOM that we created, this 2-position connector will take in, that 2-position connector will be what powers VDD and VSS. Okay, so we say, okay, well that probably would want to be over here. Now, then I say there's these bushing connections to the DC side cap. All right. In this image right here, and we haven't really talked about this guy yet, but there we need a big capacitor typically on that DC bus to make this thing work. All right, we'll talk more about why that is. That capacitor is a big, beefy electrolytic. Because of that, all right, we don't want to occupy a bunch of board space with that capacitor, and I don't want you guys making a mistake and blowing it up. All right, so that capacitor is going to be off board. Because it's going to be off board, what we're telling you to do is to put these bushing connections, all right, that'll be there. So basically what these guys are, if you look at, here's the picture of them here, right? So it says a 1-position bushing connector. What this guy is basically a threaded connector. So you can basically put a screw through this and you can connect a wire off to a capacitor or to another board, all right? So essentially what you would have is 1 bushing. In fact, let me just, we'll draw it here, okay? So there would be 1 bushing that would be here, and there would be 1 bushing that would be here. That way you can connect both terminals, all right, to the capacitor, okay? All right, let me keep going, all right? So talked about the PV power, talked about the bushing. All right, now the inductor. All right, so if I talk about the inductor, okay, so because of the fact that I'm building a full bridge, so the way that I have C right here on the fast leg, I will also have a C like this on the slow leg. So I can go down to here. So this would go to one side of inductor, so 2L, all right? Then on the slow leg and the fast leg, both have their midpoint going to the inductor. That's why there's 2 leads coming off of here, okay? Now, if you watch the video and you look at the lecture notes on the full bridge and how we use it, what we said is we actually put 2 inductors. We use 2 inductors in series. There's actually 2 inductors on here. So what we have is 2 wires going to the inductor and 2 wires coming back. Okay. So effectively what we're trying to implement is, let me draw it. Oops. Effectively what we have is this. I have L, capacitor L, all right, and this is L over 2. This is L over 2. So this is to one midpoint, and this is to the other midpoint, all right? So this point and this point go back to the board. The capacitor is on the board. And then you have a set of connection points to connect to a load, all right? So if I look at the LC filter, there is point 1 and point 2. Those are both connected to midpoints. Then there are these outputs from the inductor that come back to the board, okay? And we can then connect to a load, all right? So what I see here is I see what we told you to do is soldered connections, all right, to go to the inductor. And then we can go into a another connector here to be able to connect in both the inductor and a load. Okay, and then the capacitor will be on the board itself. Okay, so to do that connector, this is a 2-position connector, right? Because there's 2 leads coming in from the inductor, right, and then 2 going out to the load. Technically that's 4 connections, but you can fit 2 into 1 position. So for that, we have this 2-position AC output connector here, right? So you guys will use this. You'll be able to fit nice beefy wires into there, Okay, so we have a connector at the output side across that capacitor. All right, and then we say make soldered connections between the inductor and the midpoints. Okay, all right, now we have two things left. We have the power for the signal conditioning circuits. All right, that is also power for the control circuits. So in other words, the power, this 12 volts in ground, all right, that 12 volts in ground that goes, that is required by both legs drivers, all right, can come from, well, it can come from this connector, right? So power to the input side of those isolated power supplies can come through this connector. Now, because I also say power for the signal conditioning circuits, remember that your signal conditioning circuits, which are op amps, need plus 12, minus 12, and ground. Okay, so I need plus 12 and ground for the control circuits, for the drivers, and I need plus 12, minus 12, and ground for the op amps. And so we tell you to use this 3-position connector, right? So I can put in plus 12, minus 12, and ground. Okay. Now, the other element that I need, the signals to and from the microcontroller, right? The signals to and from the microcontroller, what do I need there? Well, I'm going to need 3 volts in ground, right, to power up the isolators. And then I'm going to need, if I think about this carefully, for each leg, I need 3 signals coming in, all right? So I would need the same thing for the other leg, another 3 signals coming in. I also am going to have 2 types of measurement circuits, right? I have one that's measuring the voltage on the DC bus and one that's measuring the current on the bus. So for each one of those, I have a set of connectors, all right? So in that case, right, if I think about what I'm going to have, so if I think about that, I guess what I'm going to call a signal connector. All right, what am I going to have? I'm going to have my V, so V, PV, IPV. Both of these are to the micro. And then I have 3.3 volts. All right, I'm going to have my PWM top, PWM bottom, and shutdown. And then I need to repeat that. So I need to do it for the fast side, and then I need to repeat that for the slow side. Slow, slow, and slow. Okay, so that tells me I need 1, 2, 3, 4, 5, 6, 7, 8, 9 connections in that signal connector. Each one of these gets a complementary ground. So that means I need ultimately a 2-row, so I need a header, I'll say it this way, header with 2 rows, 9 columns. All right. And this is, you guys used this before, this should be a 0.1 inch or 100 mil male header. Okay, all right, and that's how you'll connect over to your microcontroller. Okay, so again, so 2 rows, 9 columns. Am I right about 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so 9 columns, 2 rows. Okay, so hopefully that explains all of the connector business. Okay, so the thing to remember, this power for the signal conditioning circuits, it also powers the input side of the gate driver circuits. Okay, so this guy needs to have 12 volts ground to minus 12. This guy needs to have the DC bus positive and the DC bus negative. The bushings are how we connect over to that DC side capacitor. We solder in the 2 input leads of the inductor, and then the 2 output leads of the inductor and the load both connect into a connector that'll be 2 positions, right? And so all of those connectors that we tell you to use are here. Now, one element that we included, all right, we specifically tell you that across the DC bus and for the LCL cap, we want you to use these 10 microfarad 50 volt surface mount capacitors. You will need to look up their footprint. All right, so just to be clear, if I go here, that 10 microfarad capacitor is on the board. Let me erase this stuff. That 10 microfarads is on the board like that. So what I'm saying is there's one surface mount capacitor that is on the board in parallel with this guy, and then there is a separate capacitor that is off the board. Okay, we'll see why we need to do this, right? These capacitors serve different functions, right? We'll talk more about that, right? But I want that capacitor to be forced in parallel with this guy, all right? So I'm explicitly saying that bus capacitor, all right, and the LCL capacitor should be surface mount capacitors, 10 microfarads, 50 volts, like what I've shown here. All right, that's a lot of stuff, but hopefully that helps to understand a little bit more about what's going on, and it'll help you with your layouts.